Hello, everyone, and welcome to our presentation. We're going to be presenting today on secure person-to-person encrypted messaging applications. Here, we're going to be using RSA encryption for secured communication. And our presenters are going to be Joseph, me, we have Corey, we have Abdurrahim, and we have Joker. Yes, hands-on demo, Joker and Corey are going to be doing it, but then they are going to be using the Python code implemented as a secure person-to-person encrypted messages application using the RSA encryption from the sender to the receiver. We're going to see actually how it will be done. I'm not going to explain it very well, but then you are going to pay attention and see what they are going to do to explain it to us in real time. How is the process being formed? The initialization of the process, they're going to prepare the environment. And what to note here, ladies and gentlemen, that we are going to be using the operating system that will be Windows, the PowerShell, we have Linux, virtual machine, and we're going to have Mac that can use. We're going to create two parts, as you already know, of the sender and the receiver. So I'll be sending the encrypted messages, and the receiver will be decrypting the message. Okay, the setup is very, very simple. I'm going to say a very setup I'm going to do. That first of all, going to do the checking. I'm going to do the load and generate the RSA key. This RSA key will be used, the public key that we're going to use for the inscription. And again, we're going to use the private key for decryption. Load user identity from the configuration so that nobody decrypts this as it goes along the line. Thank you so much. My next person will take it.
Hey everyone, this is Abdurrahim, and I'll be taking it from here. So the background listener runs in a separate thread. It then opens a socket on the default port, followed by a key exchange, also known as a handshake. It also receives encrypted messages, and lastly stores messages as .bin files. So moving forward, we'll look at the steps to ensure secure communication. So it validates the recipient IP, ensures the message size limit. It then connects to the recipient. It encrypts using the recipient's public key, and only the recipient can decrypt the message. So for mailbox management, it lists stored messages, reads encrypted files, decrypts using the private key. It also displays the sender and the timestamp, and handles decryption failure. So for user interface loop, it displays the dashboard such as the IP, the status, the inbox, and it waits for user input. It then executes the selected actions, and it runs continuously until exit. So here are our references. Thank you all for listening, and I'll now pass it on to Corey and Nesteha.
The application's encryption goes through the crypto.py module. The module is organized into four main sections: key generation, OAEP padding, encrypt-decrypt, and key management. Key generation handles creating the RSA key pairs. The OAEP padding section secures the plain text before encryption. Encrypt and decrypt are the main functions that actually protect and recover the messages. Key management covers how we serialize, store, and identify keys using PEM format and SHA-256 fingerprints. Key generation starts by creating two large random prime numbers using a function called Miller-Robin. This function is a probabilistic primality test. 40 rounds are run, which makes the odds of a false positive effectively zero. Once we have the two primes, P and Q, we multiply them together to get the public modulus n, which is a 4096-bit key in the case of our application. The public exponent e is set to 65,537 or 2 to the 16th power, which is standard across most RSA implementations. The private exponent D is then derived as the modular inverse of E, and we also pre-compute 3 extra values for the Chinese remainder theorem, which helps speed up the decryption by about 4 times. Before we encrypt anything, we apply OAEP padding to the plaintext. The reason for this is that raw RSA is deterministic. That means that if you encrypt the same message twice, you get the same ciphertext both times. OAEP fixes this by mixing in random bits and running everything through SHA-256 and a mask generation function. This makes every ciphertext unique, even for identical messages. For the encryption itself, we OAEP encode the message and then raise it to the power of E mod n using the recipient's public key. Decryption reverses that by using the private key with the Chinese remainder theorem optimization previously mentioned, then strips off the OAEP padding. At the bottom, you can see the key data structure. Public and private keys are immutable data classes with PEM serialization built in. And we use a SHA-256 fingerprint function to create compact key identifiers for message headers. To summarize the application flow, step 1, generate a key pair. Step 2, the sender encrypts a message using the recipient's public key. Step 3, the recipient decrypts it with their private key, and all of this runs in just 3 standard library modules. POW, the POW module for the modular math, secrets module for randomness, and hashlib modules for SHA-256.
Hi, I'm Nastia Joker, and I'll be giving a little demo on our messaging application. So after we run our program, this is what it will look like, and then already configured it. So here we're going to focus on the encryption of the messages, the decryption of the messages, and the the key pairs. If we were to change it, what would happen? So the first thing we want to do is to see if our encryption is working. So we are going to start with that. So here, I'll change it to our messaging folder and see if the encryption is indeed working, basically encrypting our messages. So I'll start with the latest message that we have here. So as you can see, the message has been encrypted. So encryption part is working. So let's move on to our decryption. So in the decryption, so we're going to view our mailbox to see the message. So option 4. So if we're looking at the message, it will read the scribbled bytes and then use our private key to decrypt it. So if it's successful, it will show you the plain text of that message. So here we're going to choose the latest one. Just a second. As you can see here, the decryption was successful because it was able to use our private key and decrypt it. So let's see what will happen if we were to generate a new key pair and see if the decryption will be successful or not. So logically, it's supposed to fail. So and show you the acceptance because it's no longer going to match the key. So we're going to do a demo for that. So let's say we're going to generate a new key pair. I will say this will warning, this will replace your existing key pair. Obviously, any previously received messages will become unreadable. So we want to see this in action. So I'll say yes. So it's generating a new key pair. So let's wait for a few. And I'll say continue. So not that it has generated a new key pair, we want to see if it's going to fail or not. So we're going to say view our mailbox again. So enter the message to read. Let's go back to that. And then as you can see here, it's just going to show you the row hex data because it no longer matches the key pair. So the key pair are not matching up. So because of that, it's supposed to fail. So yeah, this is a little demo on our decrypt messaging application. Thank you.